Hey Robert, so the executor framework, this thread pool stuff is cool. How does it work in practice? Like real-world examples?
Yeah, imagine you're downloading multiple images from different servers. You could create a thread for each image, but managing those threads manually can be a real headache. The executor framework takes care of it all.
So, it handles creating and managing threads automatically?
Exactly. It pools threads, adjusts as needed, and even recreates threads if necessary. It's super efficient.
But what if you need super fine-grained control over threads? Like you want total control over their priority?
Excellent point. The executor framework isn't the ultimate solution for everything. Sometimes you'll need that explicit control, and then a handwritten solution can be appropriate.
Okay, I see. So the futures, they make asynchronous tasks easier?
Futures allow you to execute tasks independently and wait for their results later, without blocking the main thread.
How does it prevent blocking the main thread?
It's non-blocking. You submit a task, and the executor manages it. Your main application continues its processing.
So, when should you not use the executor framework?
Well, when you need precise, low-level thread management. That's a good case for a handwritten thread pool. Also, in some highly specialized scenarios, a custom approach may deliver better performance.
Wow, that's clear now. So, essentially, the executor framework is a smart tool for most common scenarios.
Precisely. It makes concurrent programming easier, safer, and often more efficient.
And is this tied to other programming concepts?
Absolutely. The executor framework often works well with other patterns, like reactive programming. However, understanding those patterns helps to choose the best approach.
Interesting. Thanks, Robert. So, what do you recommend for a new programmer?
Master the executor framework first. It is a fantastic starting point, and for most cases, you won't need to manually manage threads.
Great insight. Thanks, Robert. Robert, thanks for joining us today. We're diving into clean code, and I'm fascinated by these non-blocking solutions.
Glad to be here, Andrew. Non-blocking is a powerful technique, but it's not a silver bullet.
So, what's the core idea behind non-blocking?
It's about avoiding locks. Imagine multiple people trying to update a shared document. Synchronized blocks are like a single door, only one person can enter at a time. Non-blocking is like everyone has a key.
This sounds efficient. But how does this work?
Compare and swap. The system checks if the value has changed since the last check, and if not, the update happens atomically.
Atomically?
Yes, like a single, indivisible operation. So no interruption is possible. This is usually much faster than locking.
But what if another thread gets in the way?
The system tries again until successful. It's like checking for a parking space and retrying until you find one.
Interesting. So, this optimistic approach has advantages, but
there can be some drawbacks in complex scenarios and increased code complexity.
can you give me a real-world example?
In a server handling concurrent requests, non-blocking techniques can improve overall throughput and response times.
That makes sense. So, when should you use non-blocking?
When you have high contention, and when you can handle the complexity.
What if contention is low?
Synchronized can still be a good approach. It's about careful consideration of trade-offs.
Gotcha. Thanks, Robert. This is really helpful.
You're welcome, Andrew.
Thanks again, Robert.
Anytime.
Hey, Robert, we've talked about concurrency a bit, but I'm wondering about the practical implications of choosing non-thread safe classes. Can you give me a simple example?
Sure, Andrew. Imagine a simple counter, increment in a multi-threaded environment. A non-thread safe counter could end up counting incorrectly.
Well, how?
Multiple threads trying to increment at the same time could miss updates, or a thread could be interrupted midway, leading to a corrupted value.
So, are all Java.util collections inherently bad?
Not all, but many are not thread safe.
That's alarming. How do we fix this?
Use synchronized blocks, or specialized thread-safe collections, like concurrent hashmap. They handle concurrency under the hood.
Can you elaborate on the difference between those two approaches?
Client-based locking, synchronized blocks, is manual, and you need to lock the relevant resources in the code, making sure all threads lock the resource before accessing it.
Is this expensive in terms of performance?
Yes, Locking can be performance-intensive in high-concurrency environments.
Then what are the advantages of client-based locking?
Client-based locking gives you fine-grained control, and you know exactly where to put the locks.
So, using thread-safe collections is usually the better choice?
Often, yes, unless you have very specific performance needs that outweigh the benefits of automatic thread safety.
Got it. Are there specific libraries or frameworks that offer guidance on thread safety?
Absolutely. Many well-established frameworks will handle thread safety for you so you can focus on building the app's core logic.
That makes sense. Can you give a quick example of a thread-safe collection in action?
Sure. Concurrent hash map is thread-safe, allowing multiple threads to access it safely and without locking.
That makes things much clearer. Thanks.
You're welcome.
Hey, Robert. Thanks for joining us today. We're diving into the fascinating world of clean concurrent code. This example of the integer iterator, a simple iterator, seems like a great way to expose some subtle issues. What's the deal with race conditions?
Yeah, Andrew, it's a bit like a game of hot potato. If two threads are both grabbing and modifying a shared resource, a race condition is when the outcome depends on who grabs the resource when. Synchronization, like putting the hot potato in a safe spot, helps, but not always with multiple actions. The example shows a problem where multiple methods are involved, leading to potentially weird or erroneous behavior.
So, two threads trying to use this integer iterator simultaneously. The problem is that the methods, despite being synchronized, somehow lead to problems. Can you explain how?
Exactly. The hasNext method checks if there are more values and next fetches the next value. While each method is synchronized, the problem comes in how they are used together. A thread might check if there's a value, get preempted, and then another thread comes along, grabs the value, and then the condition to look for a value changes. The first thread comes back and gets a result that's incorrect, based on an out-of-date state.
Whoa. So, it's not enough to lock each method. You have to lock the interaction between them?
Precisely. This is the essence of concurrent programming. You need to manage the interactions or the workflow of the methods together, not just individual ones. Think of a queue with different processors working on it.
So, what are our solutions?
You've got client-based locking and server-based locking. Client-based, you protect the client's interactions with a lock. Server-based, you alter the server itself. Different use cases need different strategies. Client-based locks can be simpler in the short term.
Server-side locks sound like a possible way to prevent this problem.
Client-based is simpler sometimes, but server-based gives you control over the interaction.
So, the design is crucial, not just the individual code blocks.
Absolutely, Andrew. You need to anticipate these potential race conditions when designing the code. Consider the sequence of operations and how threads will interact.
Thanks for breaking that down, Robert. That was super helpful.
You're welcome, Andrew.
Hey, Robert. Thanks for joining us today. We've been talking about writing clean code, and this idea of client-based locking keeps popping up. It sounds like a really bad idea. Can you explain why?
Yeah, Andrew, client-side locking is generally a really bad practice. It's like handing each customer a lock to use on the same bathroom. What happens when two people want to use it simultaneously?
Exactly. So, what's the alternative?
Server-side locking. That way, only one person is ever allowed in at a time. It handles all the synchronization issues.
Got it. But in the example, why did that original system have so many client-side locks?
It was likely a legacy system. The code may have already existed before better techniques were understood. There was no automated approach for finding and fixing concurrency issues.
Wow. So, just one bad lock can cause all kinds of problems?
Absolutely. Imagine hundreds of data entry clerks, each trying to update the same shared resource, like a union's dues posting system. If one clerk isn't properly locking the resource, you'll get these weird, sporadic errors.
Like the unexpected terminal freezes?
Exactly. And finding the source of that error would be like searching for a needle in a haystack, especially with no automated tools. So, why not just avoid client-side locking entirely?
You're saying it's better to synchronize the resource on the server side?
It's usually much safer. You avoid these complex, error-prone situations.
So, why is client-side locking such a big deal now that we have robust tools?
Client-side locks create single points of failure and are more error-prone.
Interesting. It seems like those older systems faced a lot more challenges when debugging than we do now.
Yeah, absolutely. We have so much more sophisticated tools and techniques now to handle those kinds of issues.
It really makes me appreciate the evolution of software engineering.
Absolutely. Software development has become much better in the last decades, thanks to sophisticated tools and practices. The lesson is, if you can, avoid client-side locks at all cost.
Robert, you mentioned server-based locking. Can you give us a real-world example where this technique shines?
Sure. Imagine a high-traffic e-commerce website. Users are adding items to their carts, and these actions need to be processed efficiently. Client-based locking, where each client locks the server's cart data, becomes a bottleneck. This is where server-based locking really helps by centralizing the locking mechanism.
So the server handles the locking, and the client just requests?
Precisely. The server's iterator, like the one we were talking about, is synchronized. Clients don't need to worry about the internal implementation. They just ask for the next item, and the server safely manages the access.
But what if, say, the server's code is not under my control?
Then, we have a few options. The adapter pattern allows you to wrap the existing code in a thread-safe version.
Can you give me a code snippet example of that?
Quickly writes, well, we can use an adapter. Let's say the existing integer iterator is not thread-safe. This adapter adds synchronization.
Ah, I see. So the adapter, in essence, gives you the safety, even though the underlying code wasn't designed for multiple threads.
Correct. You use the synchronized keyword to block any concurrent requests when the underlying object is in use. Alternatively, using a thread-safe collection from a library like Java's concurrent package could often be a cleaner solution if possible.
That makes sense. So, server-based locking reduces complexity and error on the client side. It's all about abstraction.
Absolutely. The key is centralizing the locking logic. This approach also often leads to better performance, avoiding unnecessary overhead on every client request.
This sounds like a lot better approach than making each client manage locks.
Precisely. It simplifies the client code significantly and drastically reduces the chance of introducing concurrency bugs.
That's incredible, Robert. You've made a strong case for server-based locking.
Thanks, Andrew. It's a powerful concept for designing robust and scalable applications.
I think this will be useful in my next project. Okay, Robert. So this code snippet shows a Pagelterator class. It looks like it's designed to fetch web pages concurrently. How does this achieve thread safety?
Yeah, crucial for preventing data corruption when multiple threads try to access the same resources. The synchronized keyword around the getPageFor method in Pagelterator is key.
So, why just that part? Why not synchronize the whole thing?
Exactly, you want to limit the scope of synchronized. Imagine if the whole class was synchronized. Every thread trying to grab a page would have to wait for every other thread. That's a huge performance hit.
So, you mean this code has lock contention or a race condition?
Absolutely. Lock contention occurs when multiple threads are competing for the same lock. This slows down the application's overall throughput.
But is this the best approach? Any examples of alternative patterns?
You could use different locking mechanisms, like a lock-free approach when appropriate.
So there could be more approaches for better concurrency control?
Absolutely. You could use read-write locks to improve performance if the program mostly reads but sometimes updates data. But you'd need more complexity than this simple code snippet.
Can you give an example of a potential race condition in this code?
Sure, if two threads try to grab the next URL at the same time, they could potentially both return the same URL and process it.
So this limits the risk of duplicated work or data corruption, right?
Precisely. It ensures only one thread handles a URL at a time.
So this is important for maintaining data consistency when multiple threads access shared resources.
That's the beauty of proper threading.
So this is about balancing performance with safety.
Exactly.
Hey, Robert, so we're looking at single-threaded processing. This calculation seems pretty straightforward, but what are the practical implications?
Yeah, it's simple, but very foundational. The time to get a page and the time to parse it are independent. So if you have 100 pages, it's a linear calculation. 1.5 100 is equal to 150 seconds.
150 seconds? That seems, well, awfully slow. Are there ever scenarios where this kind of processing is acceptable?
Absolutely. If the processing itself is really quick, or if I/O is mostly the issue, single threads can be perfectly acceptable. Think of a situation where the database query itself is very fast. Often it's the latency of reading from storage.
But what if I/O is much, much slower?
Then multithreading is crucial. It's like having multiple helpers getting the data while another one does the work. You'd find it is much faster and more usable. One task can take 150 seconds, but another task can be completed in 5 seconds by splitting the workload.
So, you're saying that the 100% CPU assumption is a bit of an oversimplification?
Exactly. Real-world code has a lot of hidden delays and context switches. CPU efficiency is impacted by the OS too.
Okay, so if the processing time is 100% CPU bound, it's crucial to consider how to break up the work into smaller tasks.
Right. Think about image processing or string manipulations, heavy CPU work. Multithreading shines here. Often concurrency can be even better for smaller tasks that don't really use the full processing power of the CPU. And what constitutes a smaller task is sometimes application-specific.
So for web scraping, where I/O dominates, single threading could still work?
Absolutely.
This is quite interesting. Thanks, Robert.
You're welcome. Now, what other questions do you have?
Hey, Robert, so we're talking about writing efficient code, right? Optimization, you know?
Yeah, Andrew. A crucial aspect. And today, we're looking at how multithreading can supercharge throughput in certain tasks.
Well, multithreading? How does that work exactly?
Imagine you're reading a book, pages equals data. You can either read one page at a time, single thread, or you can read multiple pages concurrently.
So, like multiple readers at once?
Exactly. With multiple threads, you can overlap reading with processing. Think of parsing the page content while you're grabbing the next one. This really accelerates the process, like a well-oiled machine.
So, if we have 3 threads,
Theoretically, it could triple your throughput. If it takes a second to read a page, you could theoretically parse 3 pages simultaneously.
wow, sounds great. But what about real-world limitations?
There's always overhead. Managing those threads requires time. Also, if the data access isn't properly synchronized, you could run into conflicts.
That makes sense. So there's a sweet spot.
Exactly. More threads don't always equal more speed. It's about balancing the task complexity and the number of threads.
Great point. So, a big database, lots of complex parsing. How does that play into it?
That can become really intricate, the scaling. We'd have to analyze where the bottleneck actually is. Just throwing more threads at it might not be the solution.
Makes perfect sense,
We have to make smart choices when choosing the architecture for data processing.
So, instead of just blindly adding threads, it's about smart scheduling?
Right, careful consideration of the specifics of the job.
Thanks, Robert. Very helpful. Hey, Robert, great to have you back. We've been talking about building robust applications, and the concept of deadlock just popped up. It sounds like a pretty nasty problem.
Yeah, it's a common pitfall. Deadlock is when 2 or more processes are blocked indefinitely, waiting for each other to release resources.
So, like a complete standstill?
Exactly. A classic scenario involves shared resources, like database connections and message queues.
Can you give an example?
Sure. Imagine 2 threads, one trying to create something and the other trying to update it. Both need database and MQ connections.
Okay, I see.
If things go wrong, they can get stuck. One thread waits on the other to release the resources it needs.
So it's kind of like a traffic jam in the system?
Exactly. And there are 4 specific conditions that have to be met for this to happen. First, mutual exclusion.
Mutual exclusion? Like, only one thread can use the resource at a time?
Precisely. The second is lock and wait, where one thread holds a resource and is waiting for another.
That makes sense. And no preemption means one thread can't just take a resource from another?
Correct. The fourth is circular wait. Imagine threads forming a circle, each waiting for the one in front.
Whoa. So, if we break any of those conditions, the deadlock can't happen.
Exactly. That's the key to avoiding it.
Is this a super common issue? Does it pop up every day in production code?
It's not every day, but it happens. Often, it's not a perfect deadlock, but more of a performance degradation where things grind to a halt over time.
Interesting. So, it's not always obvious.
Exactly. That's why debugging is so hard. It often takes weeks to reproduce the conditions.
That makes total sense.
It's a very frustrating problem.
So how do developers prevent this from occurring?
You have to think about resource acquisition in a consistent order, or make sure you always release the resources in the opposite order to how you acquire them.
Thanks, Robert. That was enlightening.
My pleasure.
So, Robert, you're saying sometimes it's better to not force mutual exclusion? That seems counterintuitive.
Yeah, Andrew. It's a balancing act. Sometimes, forcing mutual exclusion is like putting a traffic jam on the highway. It slows everything down. If you can design your system so multiple threads can work with the same data at the same time, without creating any conflicts.
But how do you know when simultaneous access is safe? And isn't that just asking for trouble?
Exactly. That's where the key is: atomic operations. They're like well-regulated traffic lights, making sure everything's synchronized at the level of individual operations rather than the entire resource. Atomic integer, for example, ensures that incrementing or decrementing is an atomic operation. You're not having multiple threads fighting over a single value.
Okay, so you're saying that using atomic operations is safer.
Potentially. It dramatically reduces the risk, but not eliminate it entirely. You absolutely have to analyze carefully how the data is used.
What if the resources aren't atomic?
Then you have to check if they're all available before accessing them. That's where things can get tricky. The moment you have a dependent resource, the strategy breaks down.
Like in a complex game system, where you need to load resources in order, with a specific order?
Exactly. Then, you're basically back to using locks or mutexes.
I see. So, the choice depends on the specifics of the application.
Absolutely. There's no one-size-fits-all solution. You have to weigh the potential performance gains against the risk of race conditions. If you can design it without the risk, great. Avoid mutual exclusion.
It feels like we're balancing speed and accuracy in the race to write clean, efficient code.
Exactly. It's about finding that sweet spot where your code performs efficiently and reliably.
Robert, thanks for this deep dive. I really appreciate it.
You're welcome, Andrew. It's a fascinating field, isn't it?
It truly is. So, listeners, if you're looking to learn more about this and other tips on writing clean code, hit that subscribe button.
Absolutely. Join us next time as we dissect another tricky coding concept.
Sounds great. Thanks, Robert.
Thanks for having me, Andrew. Have a great day.
You too.